Okay, we will discuss now how to remove the low frequency noise from ECG signal. Low frequency noise is basically what we have called earlier. It is baseline wonder. And such type of noise occurs due to the, you can say, poor contact of the electrodes with the body surface, or due to the movement of limbs, or due to respiration. Okay, so it changes the baseline of the signal. So if you have a normal ECG, you take like this, you have P wave, QRS complex, then T wave, and so on. So in case if the signal is contaminated with the baseline artifact, it will be something like this. Okay, so this maybe like this. Okay, now due to this baseline artifact or baseline wonder, there is a difficulty in the analysis of this ST segment. Okay, so like earlier we have said that in the ECG signal, your ST segment, this is PQ segment, then QRS complex, then ST segment, and then T wave. So this ST segment, it must be isoelectric, or it must be flat in line with this PQ segment. Okay, if it is elevated or it is depressed, so there is a problem of, you can say, myocardial ischemia or myocardial infarction. Okay, that means lack of blood to the heart muscles. That is a disorder or arrhythmia, you can say. Okay, so if this baseline shifts up and down due to this artifact, so there is a problem in the analysis of this ECG signal. Okay, so the very simple way to remove this baseline from the signal is that we use a first order difference operator. Okay, so first order difference operator in digital signal processing is equivalent to the first order derivative of a signal. So if you see from this Fourier theory, if you take the derivative of any signal d by dt of xt, and if you take its Fourier transform, it becomes j omega times x omega. Okay, so differentiation in time gives you a multiplication in the frequency with a factor of j omega. So if you find its frequency response, it is nothing but omega. Okay, it means you have a system like this, with the gain of the system is linearly increasing with frequency. Okay, so you can say, okay, this is a sort of a high pass filter, because at DC frequency the gain is 0, so it is completely attenuated by this system, and as you increase the frequency, the gain starts increasing linearly with respect to frequency. Okay, so lower frequencies, they are somehow attenuated by it, and the higher frequencies, they are amplified. Right, now in the, so this type of operator you can use to attenuate or remove the DC frequencies, and you can attenuate the lower frequencies, like in the baseline wonder in the ECG signal. So the digital counterpart of this is the first order derivative, which is yn is 1 by t xn minus x of n minus 1, first order difference. And if you this, if you take the z transform of this, the transfer function, you take it as yz is 1 by t x of z minus z inverse to xz. So yz by xz, which is the transfer function, it is 1 by t 1 minus inverse. Okay, so such type of filter has a transfer function like this. So if you see that it has a 0 at z is equal to 1. Okay, so z is equal to 1 means it is the DC frequency. So at DC frequency, 0 frequency, it has a 0. So the DC frequency is stopped by this system. And if you see its frequency response at omega, it is 1 by t 1 minus e raised to power minus j omega. So it becomes, if you take e raised to power minus j omega by 2 as common, it will be e raised to power j omega by 2 minus e raised to power minus j omega by 2. And then if you divide with 2j and multiply with 2j here, it becomes a sine function. So ultimately you get h omega is equal to 2j into e raised to power minus j omega by 2 by t into sine of omega by 2. So its magnitude response will be 2 by t mod of sine omega by 2, and its phase response will be minus omega by 2, and because of this j you will get pi by 2, so pi by 2 minus omega by 2. Okay, this is the magnitude response. So if you plot it, the magnitude response of the system is mod h omega is equal to 2 by t sine of omega by 2 mod. Okay, so if you plot it, omega and mod of h omega, so it's a sine function. Okay, so at omega is equal to pi, when omega is pi, it becomes sine of pi by 2, that is sine of pi by 2 is 1. Okay, so it will go from 0 and it will end up at omega is equal to pi, it will become 1. Okay, this is the frequency response. So since the DC frequency is 0, so it is blocked, and at higher frequencies the gain is increasing, okay, according to the sine function. So if you plot in terms of frequency or hertz, this magnitude of f, so omega is equal to pi, this frequency, this corresponds, this angular digital frequency corresponds to an analog frequency of f is equal to fs by 2. Okay, because omega is 2 pi f by fs. So when is ff, when your f is equal to fs by 2, you get omega is equal to pi. Okay, so if the sampling frequency for any signal is given, suppose you take a sampling frequency of 1 kilohertz, that is 1000 hertz. Okay, so fs by 2 will be 500 hertz. So this plot is sine wave is basically graph like this. So from 0 to 500 hertz, its shape will be like this. It will be a sine function. Okay, so 0 frequency is stopped. At lower frequencies we have very small gain, so they are attenuated. Okay, so in fact all the frequencies at the frequency which is fs by 2, so that is at that point we have your gain is 1. So what you can see from this is that, so as the frequencies go on increasing, the gain of this system, it starts increasing. So it means if there is some high frequency noise in the signal itself, anyhow it will suppress the low frequency components like the baseline wander, but apart from that, some high frequency signals, they may get amplified. Okay, so this noise amplification problem, you can overcome this by using it somehow a different filter where you take suppose y1n as the average of two samples, output yn plus y of n minus 1. Okay, so this is the average of two output samples at n and at n minus 1, or you can write it as in terms of x, it will become 1 by 2t. Yn can be taken as now x of n plus x of n minus 1, then y of n minus 1, so this is minus x of n minus x of n, then plus x of n plus 1 minus x of n minus 2. So you will get 1 by 2t x of n minus x of n minus 2. So if you have a system like this and you find its transfer function, it will become 1 by 2 1 minus z to the power minus 2, or it will become 1 by 2, you can write it as 1 minus z inverse into 1 plus z inverse. Now see, this system has two zeros, one at z is equal to 1, another 0 at z is equal to minus. Okay, and because of the presence of two zeros, so z is equal to 1 is basically DC frequency, that is omega is equal to 0, and z is equal to minus 1 corresponds to omega is equal to pi. Okay, or in terms of the frequency, it is f is equal to 0 and omega is equal to pi is f is equal to fs by 2. So in the earlier case, your magnitude response was like this. So 0 to fs by 2, the gain was increasing. Okay, this was for the first order difference, that was for this 1 by t x of n minus x of n minus 1. This is the frequency response. So for this system, since it has two zeros, one at DC frequency, another at fs by 2, it means this 0 will pull down the response back to 0. So it will have a frequency response like this. Okay. Now at higher frequencies, the gain will start decreasing. Okay. So the noise amplification problem, which was in this case, it is somehow reduced using this. So it is sort of band pass filter now. Okay. So if you say, suppose some frequency where the gain is 0.707, so that band, so be above that band, the frequencies has a higher gain. Below that frequencies, so both lower and the higher frequencies, they are somehow attenuated in this case. Okay, but anyhow, these are not practical. What we actually decide, if you want to eliminate the baseline artifact from this ECG signal, we wish that you should have a frequency response like this. Okay, since this baseline wander is very small frequency, it is around generally up to 0.7 hertz or 0.8 hertz, less than that. It means the frequencies below 0.7 hertz, they must be attenuated, and beyond 0.7 hertz, all the frequencies, they must be passed without any attenuation. Okay, so what is the idea, or what is the practical response of the filter that we need? It should be like this. Okay. It means all these higher frequencies above 0.7 hertz, which is now the cutoff frequencies, they must be passed as it is, and the frequencies which are below 0 0.7 hertz, they must be attenuated, of course. Okay, so such a type of filter, if you can design, so that will be a practical way to remove this baseline wonder from this ECG signal. Okay, so we will see in the next class that how you can modify this transfer function, which was first order difference, that is 1 by t1 minus z inverse. We will modify this transfer function to get a frequency response like this. Okay, it means now the problem here is that you have to design a filter, or you have to modify the frequency response of this first order difference so that the low frequencies are suppressed without, you can say, distorting the shape of this ECG signal. Okay, because if you have a frequency response like this, or if you have a frequency response like this, it is not a good filter. Okay, it will suppress the low frequencies, of course, but other frequencies, they will also be get affected. As a result, the shape of the signal may get distorted. Okay, so if the ECG shape gets distorted, you will not be able to make clear judgments from that signal. Okay, so we will modify this transfer function, or we will change it to get a response like this. Okay.